So let's go ahead and get started with this example 1. We are to estimate the value of square root of 4.1 minus square root of 4. So to do this, what we want to do is think up here about this equation. We're trying to get things to match up. So ideally what we're going to do, there's a little game kind of you have to play. It's not a game, it's just how you apply the theorem. And it works in this way. The whole idea of linearization is that you take a value that's more difficult to work with, like 4 is a perfect square, so comparatively speaking, between the values of 4 and 4.1, which one is nicer to take the square root of? Well, certainly it would be the perfect square. So I'm going to go ahead and say that this value 4 is our nice value. So our nice value of x is what our a value is. So a is equal to 4. And I'm, of course, using this a in reference to the above theorem. So in this case here, if our a value, our nice value, is 4, then what is our delta x? Our delta x, or sometimes our dx, if you want to use that, this would be the amount it increased. Well, this would be 1/10, because the difference between 4.1 and 4 is 1/10. So then what would our function be here? Because we've identified what our a and delta x or dx are, but what about f? What's this function? Well, it would be what's being done to each of these values, and that is the square root. So let f of x be equal to the square root of x. Then, if we're going to use this formula, this result from the theorem, we want to fill it all in, so we need to know the derivative of f. So then f prime of x is 1 over 2 times the square root of x. So now note the following. Note that the square root of 4.1 minus the square root of 4 is exactly f of a plus our delta x minus f of a. Take a second here, pause the video if you have to see how with our choice of a and delta x, do you see how this turns into this upon substitution of this information into the function square root of x? Okay, good? Good. So that's the same, that's equivalent. So effectively what we've just done is we know what this is. So now we can say that this is approximately equal to the derivative at our a value times our change in x, delta x. So we'll say that this is approximately equal to f prime of a times delta x. Well, what is that? F prime of a is 1 over 2 square root of 4 times our 1/10, which I'll just write as a fraction. Moving up here, square root of 4.1 minus the square root of 4 is approximately equal to, and we can just simplify this. This will become 1/4 times 1/10 is 1/40. Or as a decimal, this would be 0.025. So that's the answer. There's a follow-up question that I sometimes ask for these, and the question might have just been, instead of estimating this difference, I might have just asked you to estimate the value of the square root of 4.1. Well, you would do everything that we've done so far, and you'd get this expression right here. This is approximately equal to that. So let's go ahead and do that. But what I'm going to do now is this square root of 4, I'm just going to write this as 2 because, that's what square root of 4 is. And then I'll just solve for the square root of 4.1. and we get that. So you can actually use ideas of linearization to estimate these really gross quantities, such as the square root of 4.1. Now, geometrically, what's going on here? Geometrically, we have this. It's really important to understand geometrically what linearization is doing. If I graph the square root function, so here's our square root function, then if I have some value x equals 4, I'm going to exaggerate this, so I'm going to put 4.1 over quite a bit, but get the idea. So then at this point right here, we have the equation of the tangent line. Now, do you see how the square root function and the line overlap for quite a bit of distance? Basically, everything between here and here is indistinguishable. Now, of course, if we actually, had a computer draw this, and I wasn't freehanding it, if we zoom in, really they only perfectly touch right there. This distance just gets very, very, very small. But the idea here is this gap, although we can visually see the gap, it is still very small. So even at a tenth of a distance away to the value 4.1, here our distance, our little gap is right there. So what we did for linearization was we essentially estimated the value of the square root of 4.1 by plugging in this value into the tangent line, forming the tangent line at x equals 4, the nice value. So we basically take our function, we linearize it at the nice value, the one that's easy to take the square root of, and then we plug into our tangent line equation the uglier value, because it's always easier to do some sort of linear operation, 4.1, than it is to take the square root of 4.1. So yeah, that's essentially what's happening.